Hi, this is Sean Chua. Welcome back to simplecamconcepts.com. Today we're going to discuss on the uses of a catalyst, which is to speed up the rate of a chemical reaction. Now, these concepts of catalyst is very important and students must be able to explain it clearly. Let me pull out an example, an answer that was given by a student in one of the chemistry examination, and we will discuss on that. Alright? Now, use of catalyst is to speed up chemical reaction, and the students wrote, which is quite good, that it provides an alternative pathway which involves a lower EA, meaning activation energy, such that the particles have more energy to collide. Alright, so in collision theory, this will increase the frequency of effective collisions, and thus it will increase the rate of reaction. So this was given by the student. I thought it's pretty good, except that one of the bullet point there's some issues, there's some error over there. Alright, so I'm going to use this as well as what we call a energy profile diagram to discuss on these concepts on catalyst. Alright, now the example that is drawn here is for an exothermic reaction, which means when the reactant becomes a product, alright, energy is expelled, is given off to the surrounding. So we expect the product, alright, to have less energy than the reactants. So the energy level of the product is lower than that of the reactants when you're looking at the energy y-axis. Alright, so reactants here, products here. All reactions will go through a hump like this. This hump over here, which is from the reactant level all the way to the top, alright, of the hump, is known as activation energy. Symbol is EA. Alright, this refers to the minimum amount of energy that's required for a chemical reaction to occur. So every chemical reaction have to clear this. Alright, it's like an obstacle. Right. So this is exo once again. So what happened is this A reactant. So the reaction for us right now is, let's say A becomes B. So this is the chemical reaction that happened. So A, in order to become B, you will have to pass this activation energy to the top before it can become the products. Alright, so this is activation energy. Now, there's something that I would like to discuss also. When reactants become products, there's always energy transfer. We call it enthalpy change. So in this case, you realize there's a drop in energy level. Alright, so we call this enthalpy change to be negative, which also the reason why this is exothermic. Alright, so this is energy profile diagram. Now, let's now take a look at what happened when add in a catalyst. Alright, now when adding a catalyst, it provides an alternative pathway which has a lower activation energy. So meaning this line, alright, this obstacle going to be shorter. So where's the alternative pathway? The pathway could be this. Alright, so you realize the hump to the energy level reactant is much shorter, right? So this will then what we call the EA prime, meaning the activation energy of this reaction with catalyst added. Okay, so it provides an alternative pathway, which is this. It's different from the one in red. It has a lower activation energy, as you can see. Alright. Now, is this point that I believe is wrong. When students say that particles have more energy to collide, you realize that this line, which is the energy, or represent the energy of the reactants, did not increase or decrease. It always stays the same. The only things that change is this curve over here, alright, which is the alternative pathway. But the reactant's energy level and the product's energy level did not change at all. So you cannot say that particles have more energy right now to collide, because the particles, the reactants, the reacting particles have the same amount of energy, alright, when they collide. Instead, I'll write this. Alright, I'll state that they will have now more reacting particles would have energy equal to or more than EA. Alright, more reacting particles would have now would have energy that's equal to or more than the activation energy right now. Such they will increase the frequency of effective collision and thus increase the rate of reaction. Let me go back to the energy profile diagram so that you have a clearer look. I'm going to use a purple color, alright, over here. Now, let's say A. There are 6 reacting particles over here. Your reactant A, alright? Look at the energy level itself. So let's say there's 1 over here, 1 over here, okay? 1 over here, 1 over here. Let's say there are just 6. Alright, so once they're able to go to the other side, then it becomes products. Now, let's look at the original graph, alright? The diagram without the catalyst. So we're looking at the red color. Okay, this one. In order, once again, for reactant to become products, it must be at the top of the hump in order for it to become product. So if we use the one without the catalyst, you realize out of the 6 particles in terms of energy level, there are only 2 that can clear this point. They're higher than this point. So 2 particles will be able to become product. Remember the word 2, okay, or the number 2. Now, right now, if I use a catalyst, it will have a lower activation energy by going through an alternative pathway. You realize that there will be 1, 2, 3, 4 reacting particles that's higher than this level, the top part of this diagram, this curve drawn in black, that can go over. So just now without catalyst we have 2. Now with catalyst you have 4. Don't you agree with me that you have more particles right now that have energy that's equal to or greater than the new activation energy? So this will be a more proper answer, alright, when we discuss the concepts of catalysts speeding up a chemical reaction. Okay, I hope you enjoy yourself and learn a lot from this discussion. Feel free to share this video with your friends, and I look forward to see you back in the next video. Thank you.